Okay, let me get started. Hope you can hear me okay. Today's class, we're going to move on from ray optics. So that's, reflection of light by mirrors, it's refraction of light by lenses. And we're going to move on to wave optics and phenomena of interference that we'll talk about in today's class. And then phenomena of diffraction that we'll talk about next Tuesday's class. Both of those are wave characteristics, wave properties of light. So that's the basic plan for today's class and for next class. For today's content, I'm going to first introduce interference, and we're going to talk about interference of water waves, sound waves, light waves. So we'll get to understand interference. I'm then going to talk about a famous experiment. It's called the two-slit experiment, or it's called Young's two-slit experiment. And it demonstrated for the first time interference of light. And this first experimental setup to show the interference of light. And it also led to the explanation, understanding nature of colors. So that was a big breakthrough in understanding light. And then I'm going to talk about a more natural phenomena. If you've ever seen soap bubbles, if you've ever made soap bubbles, you know that when you make soap bubbles or blow soap bubbles, you see these amazing colors, this kind of rainbow of colors in the soap bubbles. And that's actually a natural phenomena that's related to interference of light. And so those are our topics for today. So this really is today's plan here. So just to get us started, here's a picture of kind of a rainbow of colors, the entire spectrum of colors in a soap bubble floating in air. Now, there's a long history to trying to understand or try to explain the rainbow of colors in soap bubbles. So Newton and Huygens, those are two scientists we've mentioned, two famous scientists, and they speculated about the nature of light. And one of them, Newton, was on the side of light being a stream of particles. The other one, Huygens, was on the side of light being a wave, a rolling wave. But neither Newton nor Huygens were able to understand this rainbow of colors that appears in soap bubbles. Nowadays, we understand this rainbow of colors in soap bubbles as due to an effect called interference. It's interference of light. It's a wave property of light. And so that's the background, sort of background today's class. So let me start with this phenomena of interference. And let me just start by comparing the collisions of two particles and comparing the collisions of two waves. Now, the collisions of two particles we discussed in Physics 211. It's a famous example in Physics 211. And the collision of two waves we're about to discuss in Physics 213. It's a famous content of physics 213. When two particles collide to one another, they're discrete, localized, concentrated objects carrying energy and momentum. When they collide, they bounce off one another, and they share energy and momentum amongst one another. On the other hand, when two waves collide, and you can see the collision of waves, of ripples of water waves in this little picture here. When two waves collide, the waves merge together, they superimpose together, and they superimpose in a way that exhibits interference patterns, that shows interference patterns, and shows constructive interference and shows destructive interference. And that's a distinctive feature, distinctive characteristic of waves, interference of waves. And it's quite different from the collisions of particles where they just bounce off one another, they just share energy between one another, they just share momentum between one another. So I'm going to introduce a few terms. Firstly, let's talk about constructive interference and the superposition, collision of two waves. In this little sketch here, I got like wave number 1 upstairs, wave number 2 downstairs. So imagine these two of the waves in those two water waves in the last slide. If these two waves, two individual waves collide, they will superimpose with one another. And I'm picturing that superposition of the two waves here. Wave 1 adds to wave 2, wave 2 adds to wave 1 to make this superimposed wave over here on the right-hand side. And in this particular case, a crest of wave 1 occurs the same moment, location as a crest as wave 2. That builds a bigger crest in the superimposed wave. A trough in wave 1 occurs at the same moment and location as a trough in wave number 2. That builds a bigger trough in the superimposed wave. And so on and so forth. The next pair of crests at the same location and same moment build a larger superimposed crest. And the next troughs at the same location at the same moment build a larger superimposed trough. And that's constructive interference. The crests add together to make bigger crests, constructive interference. The troughs add together to make bigger troughs, constructive interference. This slide shows destructive interference. Again, this slide's about the collision of two waves, like the water waves on that slide a couple of slides ago. And those two waves collide and they superimpose with one another. But let's see how wave number 1 upstairs here and wave number 2 downstairs here superimpose with one another in this sketch. So when wave number 1 is a crest upstairs here, wave number 2 is a trough. And the crest and trough cancel one another out to greater or lesser extent. And that's what we see here in the superimposed wave. Likewise, when wave number 1 is a trough, wave number 2 is a crest. And the crest and the trough again cancel out to greater extent or lesser extent. And we see that in the superimposed wave over here. And so on and so forth. The next crest of wave 1 is accompanied by a trough of wave 2. They superimpose and destroy one another. The next trough of wave number 1 is met by a crest of wave number 2. And again, they superimpose and destroy one another. And so this is destructive interference, where the crests and waves destroy one another, and we get this resulting superimposed wave over here on the right. So that's destructive interference. There's a few terms that we use when we talk about interference and destructive constructive interference. And the two terms I want to introduce here are the term phase and the term coherence. So you get these patterns of interference, constructive, destructive interference, if you've got what we call coherent waves. And what we mean by coherent waves is the waves have the same wavelengths and the same frequencies. So that's what we mean by coherence. Two waves with the same wavelength, same frequency are coherent with one another. And then whether they combine to make constructive interference of the coherent waves, or they combine to form destructive interference of the coherent waves, is determined by the phase or the relative phase of the two waves. So if the two waves are in phase, that means that there's the crest of one wave occurs when the crest of the other wave occurs. The trough of one wave occurs when the trough of the other wave occurs. And that makes constructive interference. If the two waves are out of phase, it could mean that when the crest of one wave occurs, a trough of the other wave occurs. And the trough of the first wave occurs, the crest of the second wave occurs. And that creates the pattern of destructive interference. And so that's how we use the terms coherence, about waves having the same frequency, same wavelength, and phase, whether they're in phase, out of phase, to describe, to characterize interference patterns. Look, I'm showing it in this figure here. Let me point out a few things in this figure. Upstairs here. This is the example of constructive interference. Wave number one and wave number two crest at the same time, trough at the same time, crest at the same time. We say that they're coherent and that their phase difference is 0 degrees. They're in phase. They make a large superimposed wave because they're interfering constructively. Downstairs here, this was our example, wave number one, wave number two, where when wave number one is a crest, wave number two is a trough. When wave number one's a trough, wave number two is a crest. These waves are also coherent. They're the same wavelength, same frequency, but they're out of phase, 180 degrees out of phase. And that makes them interfere destructively and completely, and we get small or no resulting wave from that destructive interference. And so this slide really introduces these two important terms, the coherence of waves and the phase or relative phase of waves. So this picture here shows interference of two waterways. So what I did was I threw a stone into the, I dropped a stone into the water over here and simultaneously dropped a stone into the water over here. And that made two waves that emerged from where I dropped the two stones. The waves are wave fronts, sort of circular, spherical wave fronts that move out from the location of where the stones were dropped into the surrounding water, into the surrounding pond. And those two waves collide. And when those two waves collide, you can have crest meeting crest, you can have crest meeting trough, you can have trough meeting crest, and you see the destructive and constructive interference. And in these patterns here, this is the really interesting region. You see these complex patterns like weaved cloth or something like that. And those patterns correspond to locations of constructive interference and destructive interference, where crests are meeting crests or crests are meeting troughs. And the scale of those interference patterns is determined by the scale of the wavelength of the waves. In this case, the scale of the wavelengths of the waves is centimeters from crest to crest. And so the scale of the interference pattern is centimeters too. And you see this sort of weaved pattern of constructive and destructive interference on this centimeter scale size. Well, that's water waves. So here's a really interesting question, right? Water waves have wavelengths of, centimeters, water waves in a pond. Water waves in an ocean have wavelengths of meters, waves in an ocean. And so the wavelengths of water waves in a pond or in the ocean are sort of everyday scale wavelengths. And the patterns of interference are everyday scale patterns of interference. Can we observe the interference of light waves? Can we observe the constructive, destructive interference of light waves? And the question is really, can we observe that destructive, constructive interference of light waves, remembering that the wavelength of light rays is tiny. Visible light runs from 400 nanometers to 700 nanometers. That's a fraction of a micron. And so you're not going to see those interference patterns with an unaided eye. You need to develop some ingenious experiment to see those interference patterns. And it was those ingenious experiments, like two-slit experiment I'm going to talk about, that showed that light showed interference patterns and light have wave-like properties. Okay, so I'm going to talk now about this very super famous experiment. I knew I'd done that. Super famous experiment is the two-slit experiment, Young's two-slit experiment. And it was the first experiment to demonstrate wave-like property of light. Now, it's important in history, I always like to mention a little bit of history because I know you love it, that when Maxwell unified electricity and magnetism, one of the things that helped him in unifying electricity and magnetism was it was known at that time that light traveled at 3 × 10⁸ meters per second. So that was a good check on his theory. It was known at that time from this two-slit experiment that light had wave-like properties. So that was a good check on his predictions. So here's a rather busy sketch, I think, but it shows the principle of Young's two-slit experiment. So in this slide, in this overhead, let's start by focusing. I want to focus on the left-hand side here, which really shows the experimental setup. So in the two-slit experiment, there's a source of light. So, it might be a desk lamp, or might be a laser. And that light is shone onto this arrangement here, which is a barrier with 2 thin slits. So there's thin slit S1, thin slit S2, and a tiny slither of the light can pass through slit 1 and pass through slit 2. And slit 1 and slit 2 act like two coherent sources of light because it's the same wavelength, same frequency light that's passing through the two slits. So that's the source of two light waves, like the two stones I threw in the pond were two sources of water waves. This is Young's sources, clever. Young's clever sources of two sort of spherical or circular rays of light emerging from the slits. Okay, so there is a pattern of crests and troughs of light waves that emerge from slit number 1. And it's a little tricky to see in this, but they're the darker brown are the crests of light waves from the upper slit. And then there's, similarly from the lower slit, there's crests and troughs of light waves emerging from it. And the other brown color is the, so there's two shades of brown, that was clever, are emerging from the lower slit. And just like the pattern of water waves that we saw earlier, the pattern of these light waves will be such that you get this sort of fabric pattern of interference, of constructive, destructive interference. Actually, wherever you see the two lines cross, the light and brown, that'll be a location of constructive interference. Whenever you see the light and browns well separated, that's where you see destructive interference. So all these red points along this line here, you notice where those lines are crossing? That is constructive interference. All these black points along here, where the lines are far from crossing, that's destructive interference. And so that's the interference pattern that you see. Now, so that there's this whole kind of web or fabric of interference over here. What Young did was place a screen for the light to fall upon over on the right, far away from the slits. And so what happens on the screen is you get patterns of fringes, we call them. You get patterns of interference. When two crests arrive, like here, that's going to be a constructive interference. You're going to see bright light. Also here, the two crests arrive together. You're going to get constructive interference. You're going to see bright light here. Right in the center, you're going to see bright light too, because the two waves, crests, arrive at the same time. And the similar pattern below here. Here's another location of constructive interference. Crest and crest arriving at the same time. And here, crest and crest arriving at the same time. So you get these locations of bright light on the screen. And then between them, you get locations that are dark. So this region here of the screen, there, when a crest arrives from the top slit, it's a trough from the bottom slit, and vice versa. So you get destructive interference. Same here. When a crest arrives from the top slit, you get a trough from the bottom slit. You get destructive interference. And here too, and here too. And you end up with this fantastic pattern of bright and dark fringes that really reflect, really reveal the underlying interference of the light waves from the two slits. And over here on the right-hand side is a real photograph of such an interference pattern. And you see in the center a bright maxima. we're getting constructive interference. Either side of it, you see another maxima. Either side of that, you see another maxima of bright interference. And between them, you see dark interference, destructive interference. And we call the bright interference patterns bright fringes. We call the dark interference patterns, destructive interference patterns, dark fringes. And we label them. We label them with numbers. This one in the center is the 0th order maximum bright fringe. Up and below it are the 1st order bright fringes. Up and below them are the 2nd order bright fringes. And then the 2 dark fringes that are neighbors of the central bright fringe, they're called the 0th order dark fringes. And then the next ones above and below them are the 1st order dark fringes, and so on and so forth. So these numbers here, m equals 2, m equals 1, m equals 0, are just the labels that we give. So we can chat, you and I can chat about which fringe we're talking about, which bright fringe we're talking about, which dark fringe we're talking about. Well, this slide here, I'm not going to spend much time on this slide because it's really just emphasizing what I discussed on the last slide. It's just showing you examples of the different fringes. So if we look at the sketch on the far left here, this is showing you the formation of that central bright fringe. It's equal distance from the 2 slits. And so crest meets crest here, and trough meets trough, and you get the bright central fringe, m equals 0 fringe, bright fringe. Middle sketch. This is how you get the other bright fringes. In this case, right, crest is meeting crest on the screen, trough is meeting trough on the screen. Although it's not equal distances from the 2 slits, it is a particular distance where, although there's different number of wavelengths from the 2 slits, different numbers of crests and troughs from the 2 slits, still crest meets crest and trough meets trough. And so you get an nth order bright fringe. And then finally over here on the far right, this is the picture of destructive interference. Here's the location on the screen. It's different distances from the 2 slits. So it's different numbers of crests and troughs in general from the 2 slits, but it's such that for this destructive interference, when crest from the top slit is on the screen, it's a trough from the bottom slit, and vice versa. And so the difference between the paths is half units of wavelengths, not full units of wavelengths, and that's how you get the dark fringes. Okay, I want to show you a demonstration of these interference patterns. See if I can do that. So I want to, what do I want to do that? I want to share a different screen. Oh, that's my mail. Don't want to see that. This is what I wanted to show you. So in this overhead, in this movie, this is a movie involving a 2-slit experiment, but not with light, it's actually with water waves. And I'm doing it with water waves because those have centimeter scale wavelengths, and I can take a movie of that. I can't do that with light, where the light wavelengths are hundreds of nanometers. So there's actually a slit in which water waves are kind of emerging upstairs here, where my mouse is, and another slit down here, where my mouse is. And out of those two slits, like out of the two slits for the light experiment, comes these spherical waves of water or circular waves of water. And we're going to see them interfere in a fabric light interference pattern. And actually what I'm going to do, I'm going to show you them interfering, and I'm going to actually change the wavelengths of the two waves. I'm going to make it shorter, I think, to begin with, and then I'm going to go back and make it longer. And you're going to see the details of the pattern change with the wavelength of the waterway. So let's watch this. I think I'm going to speed it up. You see the pattern, the lattice pattern, the fabric pattern of crests and troughs and interference pattern. What's happening right now is I'm changing the wavelength. I'm having to change it rather slowly. I'm changing the wavelength quite slowly, but you should see the pattern shrink or change in a way. And then I'm going to change it back. It actually looks to me like I'm making this wavelength longer right now. So the pattern is kind of stretching out. The distance between dark bands and light bands is stretching out. And then here, I've done an interesting thing. Let me stop that for a moment. I'm now going to take the movie of the same situation, but with a stroboscopic camera. No expense spared here. And with the camera, I take a shot at the same frequency of the water waves. And in that way, I always see the troughs at the same location and the crests at the same location. In this way, we can see the interference pattern without it kind of rolling past us all the time, without it moving past us all the time. So let's just take a look at it here. And again, I'm going to change the wavelength. So you should see that pattern shrink, and then you're going to see that pattern elongate again. Right now it's shrinking down as I'm reducing the wavelength. And you see the dark regions of destructive interference, the bright regions of constructive interference, and you see the wavelengths getting shorter and shorter. And then I'm going to start pushing it the other way. I hope you can see that. I'm now expanding the wavelength of the water waves. And the distances between the crests, the differences between the troughs is getting larger and larger. And so this is exactly Young's two-slit experiment, exactly the way that you see the interference patterns with light. Okay, forgot what I was going to do next. I think I'm going to go back to my slides. I want to add an equation or formula to quantify the two-slit interference patterns. And so that's what's done on this slide. I'm just going to introduce this equation. And I'm getting my pen going again here. And the way I'm going to introduce the equation is to figure what we call the wave path difference. It's this distance here between the light traveling from the top slit to the screen, that's path R1, and the light traveling from the bottom slit to the screen, that's path R2. And the difference between those two paths is this distance, I called it delta, lowercase delta. And it's that distance that governs whether you're going to get destructive, constructive interference. Because if that distance is a whole number of wavelengths, you're going to get constructive interference. If it's half numbers of wavelengths, 1/2, 3/2, 5/2, you're going to get destructive interference, because that determines whether crest meets crest or crest meets trough. And so this distance is key. And you can imagine this distance here, and how many wavelengths it is related to the separation of the slits. That's this distance d. And the distance to the screen, that's this distance L. And the location on the screen that you're looking at, that's this distance Y. So D, L, and Y are kind of the parameters of your particular two-slit interference experiment. And we're going to see how D, L, and Y are related to this wave path difference, delta. And this is the formula. This is the key formula. If you look, delta is the opposite side of this right-angled triangle. The hypotenuse of this right-angled triangle is the slit separation. The angle in this right-angled triangle, I called it theta, and it's this angle in this triangle, and it's also this angle here in this similar triangle made up of the distance to the screen and the location on the screen. That is also a right-angled triangle, and it's a similar right-angled triangle. So the yellow and the orange triangles are two similar triangles. They have the same angles in them, although they have different sizes. Okay, so delta is going to be the hypotenuse times sine theta. And typically theta is small, a small angle in the two-slit experiment. And when it's a small angle, sine theta is approximately the opposite over the adjacent. Now sine theta is the hypotenuse over the adjacent. Sorry, sine theta is the opposite over the hypotenuse. But when theta is small, it's approximately the opposite over the adjacent. And the opposite and the adjacent are the parameters in the experiment. And so this, at least for small angles, is that extra distance that's traveled by the light from the bottom slit compared to the top slit. And so that's an important distance. And we're going to turn that into an equation on the next slide. But when you get dark, when you get bright interference patterns. So upstairs here, gosh. Upstairs here is when you get bright interference patterns. And downstairs here is when you get dark fringes. So you get bright interference or bright fringes when that extra distance delta that we just figured out, that's d sine theta, or d times y over L, when that extra distance is whole numbers of wavelengths. You get dark fringes or destructive interference when delta, that extra distance, is half integral numbers of wavelengths. That means 1/2 a wavelength, or 3/2 a wavelength, or 5/2 a wavelength. When that extra distance, it was d sine theta, or approximately d times y over L, is half integral numbers of wavelengths, then that's destructive interference. And so these are the two equations for Young's two-slit experiment. They tell you where the bright fringes are, where the dark fringes are in terms of the wavelength of the light that you're using, the slit separation in your experiment that you're using, D, the slit to screen distance in the experiment that you're using, L, and the location on the screen, that's the Y's. That's where the fringes, bright fringes, dark fringes appear on the screen, are the Y's. And those Y's are labeled with an M, that's the order. First order bright fringe, second order bright fringe, third order bright fringe, so on. And so this pair of equations for the dark fringes and the dark fringes and the bright fringes tells you where the fringes are in terms of the parameters of the experiment, the wavelength of the light, the slit separation, and the screen distance, all those quantities that describe your two-slit experiment. Well, this picture, let me explain. This picture shows you that interference pattern. the separations here are between bright fringes. The separations here are between dark fringes. And you're seeing this lattice-like pattern, this array-like pattern of bright and dark fringes that reflect the interference of the light waves from the two slits and reflect and are determined by the wavelength of the light, the separation of the slits, and the distance to the screen. So I want to look at an example calculation of this, if I can. Okay, so in this example, our two-slit experiment is described. So we're told that the slit separation is 2.1 millimeters. We're told that the screen distance is 1.75 meters. We're told we see on this screen, right, an interference pattern of bright and dark fringes. And we're told, look here, that there's a little over 0.5 millimeter between the first and the second order bright fringes. So it's 0.55 millimeters distance between first order bright fringe and the second order bright fringe. And we got to take that information, we told it here, summarized it here at least, and figure out the wavelength of the light, the visible light that's shining on this two-slit experiment. So let's see if we can do that. Okay, well, I just summarized again the parameters. And then I went to my equation. It's this one here. This is the equation for the bright fringes that we introduced. You get a bright fringe when this ratio of slit separation, screen distance, and location of fringe is a whole number of wavelengths. Now, in our case, we're told about bright fringe number 1 and bright fringe number 2. So that's where M is 1, bright fringe number 1, M is 2, bright fringe number 2. So we plug in, or I plugged in 1 and 2 to this equation, and I rearranged for the location of the fringe on the screen. So this says the location of bright fringe number 1 is equal to this quantity. This says the location of bright fringe number 2 is equal to this quantity. Notice there's a difference between these two equations because M is different in these two equations. It's 1 here, it's 2 here. So this is the location of the two bright fringes we're interested in. But actually, we were told the difference in their locations, the separation of their locations, rather than their actual locations. So if I just take the difference of those two equations, I get this equation here. And this involves that bright fringe separation that we're told in the problem. Well, stand back from that calculation, right? I need a rest from it, tire me out. Stand back from that calculation and I look at that formula I just made. It contains in it slit separation, well, we know that. Contains in it the screen distance, we know that. Contains in it the separation between the first, second order bright fringes, we know that. The only thing we don't know in that equation is the wavelength lambda. And so I turn that equation around, here it is, for the wavelength, in terms of the quantities that I know, the fringe separations, the slit separations, the screen distance. I plugged them all in. I got 660 nanometers for the wavelength of the light. That's a fairly long wavelength for visible light. It's red light. We were shining red light on that slit. Okay, there was an example. Oh, got a quiz question. Okay, I think we're done with the quiz. So if you increase the wavelength of the light, then you'll need a greater extra path length, that delta, for successive constructive interferences or successive destructive interferences. And so if you need a greater path length for the constructive and destructive interference, you're going to have a greater separation of the bright dark fringes on the screen. So greater wavelength of light gives a greater separation between the bright and dark fringes on the screen. I should point out here that this was a real breakthrough for several reasons when Young demonstrated this wave-like nature of light by these interference patterns. One was that he demonstrated that wave was a wave. It had wave was a wave. Light had wave-like properties. That was a big thing. The other one was that by doing the experiment with different colors of light, red light, blue light, green light, he saw that different colors of light correspond to different wavelengths of light. Red light's a long wavelength, 700 nanometers. Blue light's a short wavelength, 400 nanometers. So he realized, he suddenly understood what color was. The physics interpretation of color is, what we see as color is just our recognizing of different wavelengths of light. And so when you see all these colors in a rainbow, you're identifying the different wavelengths of light in the rainbow. And that's ultimately what color is. Okay, I want to talk about a natural phenomenon involving interference of light. And it's this natural phenomenon I mentioned at class start. If you blow, if you blow soap bubbles, we've all, let's admit it, we've all blown soap bubbles, when we were 3 or 4 or 5 or, in my teens. I was blowing soap bubbles, and they're amazing. They're absolutely amazing. You see all these bright colors in the soap bubbles. This picture here captures some of those bright colors in the soap bubbles. Why do we see this rainbow in the soap bubbles? Let's see if we can explain that with interference. And here's the explanation. And it's really quite an intriguing explanation, I think. So in this slide, I'm picturing a few things. Upstairs here, this is a soap bubble, and you're seeing all these different colors. How can we see all these different colors in the soap bubble? We're seeing them by interference in the soap bubble. And we're specifically seeing them by interference of light, of reflected light off the soap bubble. And we're seeing them because reflected light off the soap bubble is light reflected off both the outer surface of the soap bubble, the outer radius of the soap bubble, and actually the inner surface of the soap bubble, the inner radius of the soap. And so to better understand that, I made this sketch here. So in looking at this sketch, imagine I've sort of blown up some tiny region of the soap bubble. And I'm just looking at it in cross-section. And that soap bubble is some very thin film, and here's the film itself. So outside the soap bubble is air. Inside the soap bubble is air. And the soap bubble itself is made of soapy water. So this is a picture, an enlarged picture of that thin film that makes up the soap bubble. Now, I said that the way you get the interference pattern is that light is reflected off, here comes light. It's going to bounce off the soap bubble, and it's reflected off both the outer surface of the soap bubble, that's light ray number 1, and it's reflected off the inner surface of the soap bubble. That's light ray number 2. And so that's 2 light rays, 2 sources of light, like the two-slit experiment is 2 sources of light. And these are coherent light, the same wavelengths and frequency. And so they're going to interfere, and they can interfere destructively and constructively. Just like in the two-slit experiment, you get constructive, destructive interference. And when they interfere constructively and destructively, they're going to make either, if it's constructive interference, bright light, if they're going to make destructive interference, dark regions. And what determines whether it's constructive or destructive interference is how many oscillations of the light wave took place on this extra path that this second light ray took compared to this first light ray. And so this extra path is important in determining whether you got constructive, destructive interference. But actually, another point is important in determining whether you got constructive or destructive interference. And that's something you wouldn't have expected. And nobody expected this. And it was discovered in this type of experiment. So the thing that wasn't expected is that the light bouncing off the top surface, which is heading from air to water, from lower to higher refractive index, when it bounces off, when it's reflected, it incurs a phase change of 180 degrees. So a crest becomes a trough and a trough becomes a crest. When light bounces off the bottom surface, it's going from water towards air. That's from higher refractive to lower refractive index. That's the opposite. It doesn't get that phase change. There's zero phase change. And so crest stays a crest, trough stays a trough. And so these light rays, 1 and 2, can have different phases for two different reasons. One is the presence or absence of this phase change, this 180 degree or zero phase change on the reflection. And then the second one is this extra path that is taken by ray number 2 compared to ray number 1. Now you can put all those things together. The understanding that you get a phase change or you don't get a phase change on reflection, depending on whether you're going from higher to lower or lower to higher refractive index, and the fact that the second wave is traveling twice the thickness of the film, twice the thickness of the soap bubble, further than the first ray is traveling. So let's put all those pieces together. And I'm just going to quote the formulas for interference with a soap bubble. There's two formulas here, upstairs and downstairs. The top one is for constructive interference, where you get bright colors. Bottom one is for destructive interference, where you wouldn't see the color. You get bright colors when that extra distance that light ray 2 travels, that's the delta, is a half integral number of wavelengths. Not a whole number of wavelengths, a half integral number of wavelengths, because one of the reflections has a phase change, the other one didn't. You get destructive interference when that extra distance is a whole number of wavelengths. And that whole number of wavelengths is because, again, you get an extra phase change of 180 degrees for the reflection of the top surface, but not the bottom surface. So these are the conditions for constructive, destructive interference, bright and dark fringes. This lambda here, this wavelength here, though, is the wavelength in the water. And so typically we write it as the wavelength in free space or empty space by taking the wavelength in free space, empty space, and dividing by the refractive index of the soap. So that's why I've replaced the lambda subscript n in the water, in the soap, with lambda over n, the wavelength in empty space, free space. And if that distance, that extra distance here is twice the thickness of the soap bubble. And so these two little equations describe when you get bright colors, for this condition, relation between the thickness and the wavelength. And you get dark colors, you don't see the colors, when you get this relation between the thickness of the soap bubble and the wavelength of the light. So you can see here that clearly different thicknesses would produce reflection, intensive reflection of different colors. As you change the thickness, you'll change the colors you reflect. And in the soap bubble, it's made of different thicknesses. And so you get different colors. That's how you get those different colors. There's a question in the chat about whether how do you know whether to put in the half or not put in the half? And putting in the half and not putting in the half, that's a really good question. We didn't put it in, so in two-slit experiment, the half is for the destructive interference, not the constructive interference. And the half is so that you get crest meeting trough and trough meeting crest. In the thin film interference, it's the other way around. The constructive interference gets the half and the destructive interference doesn't get the half. And that's a nuisance because it's easy to mess that up. But it's because in the soap bubble case, you get an extra half, an extra phase change when you reflect off this top surface that you don't get off the bottom surface. So look, it's an unfortunate thing about these pair of equations that the halves change from bright fringe to dark fringe between the two equations, but unfortunately it's nature. Nature does that to us. I'm not trying to trick you on an exam. That's it. Blame nature for that trick. But it's a very interesting phenomenon. It's exposing that the reflected light from the top surface gets its phase changed. Okay, let me just show you a movie of this, and then I think we'll look at a quick example of this. I'm going to share another screen. So this is the soap bubble you're watching right now, and I'm waving it around underneath a lamp, and you see those intense bands of colors. That's when you're getting these conditions for destructive, constructive interference. When you see that bright pink, that extra distance traveled exactly corresponds to that condition for constructive interference. When you see the bright green or the bright yellow, those extra distances traveled are exactly that condition for constructive interference. So it's a beautiful display of the wave properties, the wave nature of light. And then finally, I think here we break the bubble. Yeah, it was a soap bubble. It really was a soap bubble. You're really seeing the wave nature of light. To me, that's a fantastic demonstration. I love it. I know that sounds over the top, but I really think it's fantastic. Okay, share screen again. I just want to end up with an example of soap bubble interference. And maybe this will help with that question about the halves or not the halves. So in this question, I'll go get the pen going again. We're imagining a soap bubble. The soap bubble is made of water, essentially, so its refractive index is 1.33. We're told it has a thickness of 120 nanometers, thickness of the walls of the soap bubble. And we got to calculate the wavelength of light that's most strongly reflected. So we got to calculate the wavelength corresponding to that that bright fringe equation, or that constructive interference equation. So let's see if we can do that. Here I wrote down what we were told in the problem. Refractive index, 1.33 for the water. Thickness, 120 nanometers for the soap bubble. And then here's an interesting point. Those equations for the constructive and the destructive interference for the soap bubble have an m in it, an integer in it. It could be the first 0th order, the first order, second order constructive interference or destructive interference. We're not told that in the problem. So as my starting point, I'm going to imagine that, let's imagine that there is a 0th order constructive interference. Now, if you do the calculation and you can't get an answer, that means that there isn't. The soap bubble is too thick for 0th order constructive interference. And so you'd have to then try m equals 1, first order constructive interference. And if you didn't find that, you'd have to try second order constructive interference. And when you have thick soap bubbles, it tends to be that you have higher orders of destructive constructive interference, and you tend to see the colors of the rainbow less clearly. But I'm going to just try and see if we see the brightest color in the rainbow. That's m equals 0 constructive interference. And so here's my calculation. Oh, there was my calculation. Gosh. Come on, pen. Here is my calculation. These are the parameters from the problem. And here is that condition for constructive interference. That extra distance traveled, that's twice the thickness of the soap bubble, is m plus a half times the wavelength of the light in vacuum divided by the refractive index of the material. Now again, I'm guessing m equals 0. We're going to see if the 0th order bright fringe does produce this condition for constructive interference. I'm going to stick in m equals 0 there. If I rearrange the equation, then I get this equation for the wavelength of the light that's going to create 0th order constructive interference. And you know, I know the refractive index of the water, and I know the thickness of the soap bubble, so I can plug them all in, and hey presto, like a magician, I get a wavelength of light, and it's 640 nanometers. That is visible light. That is red visible light. And so with this thickness of soap bubble, I see a bright fringe of red light reflected off that soap bubble. If we were to change the thickness of the soap bubble, we'd see a different color of light. And so that's how you get these patterns of interference in soap bubbles. Okay, I want to just show you one more video. I was scared I wouldn't get to the problem, so I skipped one video. You might have noticed that. I was kind of cunning about it, or clever about it, I thought, but I bet you saw that I skipped one demonstration. So let's just do that demonstration. It's a demonstration of the two-slit experiment. So that experiment that was built to demonstrate the wave-like nature of light, to demonstrate the nature of colors of light. So I'm going to show you the two-slit experiment. I'm going to share a different screen again. And I hope you can see this. And we're going to look at green light. So this is a video of the screen in a two-slit experiment where I'm shining green laser light through the two slits. and these blips are the bright fringes, and between them are the dark fringes. And this is for a particular slit separation. And then I'm going to start changing the slit separation. Now I've changed it, and the blips are getting closer together. And so that's showing you how the pattern depends on the slit separation. And then I'm going to go back in the opposite direction with the slit separation. I think this is the largest slit separation, and now I'm going to make the slit separations smaller again. So as I make them smaller, I get greater distances between the bright and dark fringes, because I always need a certain path length to get the constructive destructive interference of the bright and dark fringes. And then I'm going to do the same thing with red light. So red light has a longer wavelength than green light. Red light's 700 nanometers and green light's, I don't know, 500. And with the longer wavelength, then that pattern of bright and dark fringes gets stretched out. And now I'm changing the slit separation again. I'm making the slit separation larger. And we're seeing the change in the fringes. And then I'm going to make the slit separation smaller again. And you see those little spots, bright spots and dark regions of the red and the red light and the dark bands. And so that's Young's two-slit experiment. And so just to finish up, today's class was all about interference of light. We've moved on from ray optics to wave optics. We talked to begin with about the concept of interference of water waves, sound waves, light waves, destructive, constructive interference, coherence of light, the phase of light. Then we looked at a particular experiment, the two-slit experiment, that first demonstrated the wavelength nature of light. And then we looked at a natural phenomena, rainbows and soap bubbles, that also demonstrates the wave-light nature of light. And so that was the summary of today's class.